Welcome to another DDMT tutorial. This is part 2 of the Behaviour Builder series, and we're going to be talking about differential channels. So, on this kind of mock whiteboard setup, let me try and explain to you how we calculate the differential channels. You have your wave or signal in whatever channel. For example, let's just say this is X, and it rises and then falls and then it rises again. The value of the peak or the trough of the wave is not necessarily unique to that behavior, but the gradient or difference or rate of change is unique to that behavior. So we can take this value here and the value at the bottom and work out the difference. Let's put it in an equation to make it more clear. Just do the wave again. So we got a value here and a value there. So you have value of x at the peak, x1, and the value of x at the trough, x2. And the difference would be just x2 minus x1. But we want to plot the difference for every event, for every data point. And I think when we produce our differential channels, you'll understand that better. So let's show you how this might change between two behaviors. So we've just got behavior 1 and behavior 2 here, and we can say this is X again. There's the first. And the second. If we made an equation that was pick out values more than 0.9, it would find values at the top of the wave. But it would do the same thing for behavior 1 also. Even though these signals are very different to one another. But if we actually look at the difference in the channels over time, it'd be vastly different. For example, behavior 1 is changing by 1.8 or from the peak to the trough much quicker than behavior 2. I hope that background gave you a little better understanding of differential channels before we get stuck into the example. We have some goat data loaded up into DDMT. I've done my time offset, I've loaded in bookmarks, and I've just tidied up the display. You've got pressure at the top where it's been inverted to give us an idea of altitude, and then I've got the 3 acceleration axes and then VEDBA smoothed on the bottom. So let's zoom in on the bookmarks loaded up. This is a really good example here. If we just looking at the green or the y-axis, and hypothetically we wanted to pursue that to define our behavior, let's increase the amplitude. You've got clear peaks and troughs in waves here, but when the animal stands, then peaks and troughs level off. As the animal changes posture, we're left with some high values. Now, the best way to show this would just to try and define our own behavior using this y-axis. Try and get a more consistent wavelength by smoothing out the y. Take this down maybe to 10. Maybe more than that, maybe 5. So we smooth it out to 5 to try and get a more consistent wave across that channel. So okay, just a really quick equation. If acceleration y smoothed is more than 0.35, so it's picked out peaks in the step, but it's also picked out a massive area of standing because then values rise as it changes posture. So now let's try and define moving from standing using differential channels. We were looking at the Y. I'm just going to increase the amplitude of the acceleration. Let's see a bit more of the data. Now, smoothwise, even at 5, I feel like it's smoothed a bit too much. So let's even bring that down further to say 3. If I'm looking at the difference in the y-axis, I need to define how many events it needs to find that difference between. We're going to do this by looking at the peaks and the troughs of the waves. And we can just use the display to work out the difference in events. So just highlight events here. So for example, here it's about 3. There's a lot of variation in these steps. Might help if I get rid of the y-axis. I can just see the smooth now. 3 again. Seems like 3's a nice amount to go for. So let's build our differential channel. We do this by going differential channels at the top, and it opens up this control panel. First thing, we need to select the channel we want to differentiate. I'm choosing acceleration Y smoothed. Where it says differential calculated over range, we want to put 3. Next, we have calculate differential and move on by. That's the amount of events after it's calculated the differential it's going to move on by, and we're just going to leave that as 1 for now. We add our channel, and then we click process channel, and it should process here. Now the channel has a little bit of a lag in the display, so if we just wriggle the mouse wheel, now we can use these controls here to alter the channel like we would any other channel. So we can smooth it, increase the amplitude, offset. So let's just increase the amplitude to make any peaks really clear. We'll offset it up a bit to bring it away from the acceleration. Zoom out a bit to compare it against standing. Once we're happy with the position and amplitude, we can pick a nice color, maybe similar to green. Go for a dark green if we can still see it. This channel is the difference in y-axis smoothed across 3 events. As you can see, the values don't rise when he changes posture, when the goat's standing. It's just to do with these differences in wave peaks and troughs. So we can now use this to define steps. One thing we can do is we can smooth out this channel to try and get it to flatline best we can when he's stationary. I'm actually not going to smooth at all. My differentials across a short period, but play around with the smoothing. You might get more consistent wavelengths and reduce your noise. We can now go to the Behaviour Builder tab, and if we start to build an equation, we can see the channel we've made in this differential channel option here. If we click enter, click yes for now, and let's give it a value. Not only is the differential channel on the drawing, we also have values for it in the display at the bottom here. Let's look at the values that coincide with the steps. So we got highs of 0.2, lows of 0.05, and then more interestingly, when he's standing, the highest value is around 0.04. So let's say 0.06. Next step, mark events. Let's put it back to yellow again. Evaluate the expression. Set using the sample lines and click go. as you can see, it's not only picking out or making a good attempt at picking the amount of steps, but it's also not picking out the standing. Although there seems to be one false positive here, as there's a bit of a shuffle or noise in the data. And that's a really basic use of differential channels. To mark out a single step rather than mark out multiple events within the step, we can use the calculate differential and move on by within the differential channels panel. Now, we went over this really loosely the first time we built our equation, and by default we set it as 1, but it can be a really useful tool in this instance. By changing this value, it will almost add in a blind spot where it won't calculate the difference between the events until you've specified. So for example, if I set this to 3, it will calculate the difference in the y smoothed for 3 events, and then move on 3 events and calculate the difference in the y for 3 events. Seems a bit complicated, I know, but maybe if I add it and process it, it will make more sense to you. So if I just process that, if you just saw the window update, now those waves have turned more into spikes. And what we can do is we can run the equation again using this new differential channel and say I change the marked events to 1, so they'll flash up red. A couple of times, and maybe I need to adjust my equation where it's not picking out the step, but instead of giving us 3 events here, it's giving us 1 event in red. Just to make that a bit more clear, I can delete all the yellow events. It's worth noting, now you've built these differential channels, if you store your behavior, like I'm going to do here, and export the behavior, it will take the differential channel with it. It's a really useful aspect, so you don't have to rebuild your differential channels. You don't have to use differential channels across fine scales. For example, step by step. You can use differentials across larger time scales. So in this instance, I want to find when the goat is climbing and when he's walking on flat ground. For this, we're going to need pressure. It's already been inverted for me, so as pressure rises, the altitude actually drops. I'm going to smooth that across a mighty 200 events. Now let me build a differential channel using that. Once I've built my differential channel, I can then begin to build equations based on 2 parameters. One being vedba, to define when the goat is actually moving, and then the difference in pressure across 200 events, or in other words, my differential channel, to define when the goat is climbing. The equation's all built, relatively simple. Now let's run it across the whole split and see what it marks out as yellow. And it's done quite well. There's little bouts of climbing which do coincide in a change of pressure. It's really successful at picking out these big changes in pressure and also recognizing them as walking. So that's the end of the tutorial on differential channels. It was just a simple look at some very basic examples, but you can really take this to a number of levels by practicing and playing around with different channels to try and derive a range of behaviors with using that idea of frequency of wavelength, or even the gradient of a wavelength, or the gradient of a channel.